So welcome back. I believe you guys have spent some time by using the pen and paper to work on the hierarchical clustering on the data set for us to test on. Of course, you will have several points that are tied with the distance. For example, 2 and 3 has distance of 1. While that's the case, you're probably going to join them together. Because 2 and 3 are going to be joined together, the centroid, if we use the centroid concept, it will end up with 2.3, so the distance between 2.3 and 4 will be 1.5. So it's actually not going to group them right directly. Instead, 9 and 10 is probably the next closest point, so you will merge the 9 and 10 into one cluster, 11 and 12 with another cluster, and then 18, 19, because all of these are distance of 1. 23 and 24, while we're doing that, you will form basically like all of the points with distance of 1, and then we will continue doing that. So I believe you are capable of doing the hierarchical clustering. The only thing I want to emphasize on is how does computer try to work on this. So for a computer to do hierarchical clustering, this is a necessary evil. Basically, again, a distance matrix, just like k-nearest neighbor concept. So while we're doing this, we need to create a n by n, which is n square space to store the distances. Of course, the diagonal value are all 0 because the point to itself is going to be 0. And then you will need to calculate the distance basically for node of 2 with all other points, finding out the distances over there, and actually go keep working on that while you are able to fill in the whole triangle spaces over here. While we're doing that, we actually end up with all-to-all nodes distances. And now that's how computer will be able to really finding the closest point. It's not going to take a look of the data set and understand 2 and 3 has only distance of 1, so they are the closest point. So while we have the distance matrix, depending on how you write your comparison of the nodes, you try to look for the smallest value, saying that the smallest value that we found is actually the node 2 to 3 with distance of 1. There are also some other value of 1s, and again, depends on how you write your less or less equal, the equal sign. We basically saying that we find the first one, and because all of these values are not smaller than 1, so we will consider this as the 2 closest point. So when we try to do that, we will need to merge the node 2 and 3. So first of all, you can see that we try to group them together, creating a small cluster, and then we need to update the information over here. So what's happening is that we will try to merge the node 2 and 3. So you see that we need to merge the node 2 and 3, and at this time we will have one node less. So originally we have 15 nodes. Now when we try to merge 2 and 3, we will have one node shorter. So basically you can see that all the nodes in this example, we take away all the information about node 2. So that forming an updated distance matrix. So you can see that now I have a node 2 and 3 considered as one node. The distance with node 2 and 3 is 0 because of the centroid now is actually 2.5, the average of the 2 points. You can see the distance from 2.5 to 4 is actually 1.5. So we actually need to update the whole information about any information related to the point of 2 plus 3, which is the new cluster that we have over here. And that would be true for the case if we continue to work on the hierarchical clustering. You see that the next closest 2 points are actually 9 and 10. So what we need to do is that we're going to group 9 and 10 together to form another cluster. And then we need to update the information. So we delete everything about the node of 9, update the node, new node, which is 9 and 10 over here. And then we need to update all of the informations about 9 and 10. So you can see that that is the next step of the process. while we're doing hierarchical clustering, you see that we basically repeat the whole process. We try to find the next two closest points. In this case, it will be 11 and 12. So we will merge the 2 points together and then update the information about the new cluster that we have. And we will repeat this whole process until there's only one cluster left. So this is how we will be able to implement the hierarchical clustering in computer science point of view, or writing the program perspective. So this is a very simple algorithm. It's very easy to understand. And of course, during the example, we use the centroid concept to calculate the distance. We can still apply the same concepts we discussed in our previous class, which is in the k-means clustering. We can, when you calculate the distance between one cluster to the other cluster, there are many ways of doing so. The easiest way is probably using the centroid. Of course, we can still using the single link. We can still use the complete link to have different distance values between cluster and cluster. And while we apply that, the results may generate some minor changes. So these are the important things about the hierarchical clustering. So as we discussed in the beginning, hierarchical clustering has two kinds of hierarchical clustering. One is from bottom up, which is what we have seen. We build up, merge 2 points together to form a cluster, and then merge another 2 points, and then eventually we will merge cluster and build everything into one big clustering. On the other side, there's another style of the clustering, hierarchical clustering, which is divisive. What they're trying to do is basically starting to treat everything as one big cluster, and then you divide the whole thing into 2 smaller parts. The question is how? How would you be able to divide the whole thing into 2 smaller parts? And ideally, another the 2 smaller parts will divide it into another 2. So each one subcluster will divide into 2. That will, the next layer will become 4 clusters, and you can keep going on that. The major problem is, how do we divide the whole cluster into 2 clusters? This is actually a very interesting question, so that we need to discuss in the idea of the k-means clustering. So basically, k-means clustering become our best friend now, even though we just learned that last week. We can totally use k-means clustering to look into the whole cluster. And then when we assign, when k equals to 2, you will be able to get 2 clusters. So that's the way of how we divide the whole clusters into 2 smaller parts. So this is basically how we can merge the concept of k-means clustering and hierarchical clustering, which is very interesting. So this is what I plan for you guys to learn about the hierarchical clustering. After this part, what I want you guys to do is actually read the thesis that I have provided for you guys. So in this thesis, from today until Thursday, I want you guys to read the first 3 chapters. Don't feel it's a lot of reading. This is actually a thesis that generated from my previous undergraduate scholar. The paper is actually pretty easy to read. They are single column, double space. So each page has only several words to read it. So I want you guys to read the first 3 chapters, and when we come back on Thursday, I will generate another video to talk about these paper or this thesis plus a new clustering algorithm I want to introduce to you guys, which is going to be the hybrid hierarchical k-means clustering. Let me give you a brief introduction about this thesis. Basically, this is the thesis I using hierarchical clustering to do some research. So what kind of research is that? This research is actually very interesting. It's a collaboration between me and another biology professor in ULR. So what they're trying to do is they try to identify the longevity genes in yeast, which is very interesting. So what they are trying to do is that they looked into the genes of the yeast. And why yeast? Because yeast has only 5,000 genes. Compared with human, we have much more. And we can do a lot of special things about the gene, on the yeast without violating any law or anything. So biologists, what they try to do is that they look into the genes and then say that, hey, let's try on this gene. So what they're trying to do is that they knock out the genes. So basically, they just totally take the gene away, and then that yeast born without that gene. And then they try to keep track of when they knock out this gene, does this yeast live longer or live shorter or has no change? If there's no change, that means this gene is not related to their longevity. And if the gene lives longer or shorter, then that means that this gene is related to their lifespan. So that's what biologists people do. And of course, when we try to knock out our genes and we try to do that one by one, it's very time consuming. And it's actually pretty difficult to look into all of those 5,000 genes and then do 5,000 times of the experiment to identify each gene of that. So the current research suggests that there's about 10% of the genes are related to longevity. And at the time of I am doing the experiments, 10% of the 5,000 genes is about 500 genes. At the time, there's only about 100 genes has been identified as longevity genes. So there are another 400 genes has not been discovered yet, hypothetically. So how does computer science can help? How do we apply hierarchical clustering in this data set, in this kind of experiment to find possible longevity genes? Like I said, this is a very interesting topic. I want you guys to read the first 3 chapters and we will discuss more when we come back on Thursday. Enjoy the rest of the day. Be safe, wash your hands, and hopefully I will see you guys soon.